vector associated with it. There's a wave vector, a wave function associated with it. So now this wave function will tell us how is it behaving, right? It's a function. So u is what changes with respect to the wave function in the lattice. If it's going in this direction, it may have a different wave function. If it is going in this direction, it may have a different wave function associated with. So when we have this concept of wave function or directionality for the movement of electrons, then we have a deeper thing that how would be the energy change for that electron. So to that energy is what we measure in EK diagram. So this is an thing what we draw. It's a 2D plot. We call it EK diagram. So energy versus K. So K is your, uh, let me say, it's the wave function, propagation constant of the wave function. So the direction of the movement of an electron would be defined by propagation constant, wave vector. So the idea is that it's not just valence band and conduction band, it's also what direction is the electron moving. What is the propagation constant that's associated with that wave vector of an electron. So this is wave function phi of x, which depends on propagation constant and the direction of propagation, right? Now, when we bring this concept of directionality or it is direction dependent, then for different material, the conduction band and valence band, their minima and their maxima may not be right on top of each other, which means that we have materials where electron cannot just jump straight up and go to conduction band. In similar way, if an electron is coming down from conduction band to valence band, it cannot just come straight because in, in the space, their k or propagation vector would have different energy levels for them. Now, so there are simple definition for this. When the conduction band minima is directly in line with valence band minima. So these are minimum values which are close to it. We call that material as direct band gap material. And if the conduction band minima is not in line with valence band minima, which means now if an electron has to jump down, first it has to change direction and then it can jump down lower energy level. We call that indirect band gap material. So what it does is these functions tell if an electron can jump without a momentum change or not. So this k space change is associated with the loss or gain in momentum. So this one is not an energy change, it is a momentum change. Whereas this is a direct energy change. Why it is important? The whole energy that's coming out because of that change is converted into light. But in this case, the energy change is from here to here, but some of that energy is being used up here, just in the momentum change. So if I were to use a semiconductor material to make my optical system or optical device, I would choose a direct semiconductor material because all the energy change will be available as photon to me to get whatever work I'm doing with that material. Does it make sense so far? It's a new concept of direct and indirect semiconductors And it comes from this idea of that 3D lattice structure where the movement of an electron from one corner or in one direction versus another direction will have different energy change. So, and that's, if we look at this, and that explains here the periodicity of most lattice is different in various directions. So if you go back to that lattice cube concept that we introduced in the first chapter, bunch of cubes stacked next to each other. If you're going with x direction, you encounter atoms at certain distance. But if you're going in xy direction at diagonal, the next atom may be coming at later distance, more further away than in other direction. So this idea of direction has to do with the lattice, the difference in the lattice design or the lattice situation, and that results into having creating an EK diagram. So EK diagram being a diagram which has energy and wave vector or propagation vector relationship. So sorry. So this guy versus energy is what gives us how energy would change in 3D in an actual semiconductor material. All right, questions? All right, so let's continue on direct and indirect semiconductors. So if you look at basic semiconductor materials, you would see that they all, some of them are direct. So like it is showing here, it's direct, and some of them are indirect. So, oh, this is talking about diamond and zinc blend. So let me clean this. So there are some materials which are direct, like silicon is direct, gallium arsenide is indirect, aluminum arsenide is indirect. Sorry, gallium arsenide is direct. Let me write down onto this itself. This is direct. Gallium arsenide is direct. This is indirect. So different materials have different properties when it comes to their band alignment. How do we know which one is direct and which one is indirect? So we have this plots of the information of these materials, where by changing their relative composition, we can change different values of the conduction band. So here's an example where there are sub bands of conduction band are shown. So we call these other conduction band values as L. This is, I think, sigma and chi. Let me see. What do we call them? So when we have the knowledge about the values of the conduction band, basically these are the minimas of conduction band in different directions with different wave vectors, different k values. If the lowest one is lined up, we call it direct. If the lowest one is not lined up, we call it indirect. So if you are given a picture of the conduction and valence bands, you should be able to see that if The lowest one is lined up with the highest one of the valence band. You would call it as a direct band gap. It's all that's it to this concept. And the direct band gap material is what is preferred for optical devices. They are used for optical devices for the simple reason that we don't want to lose energy in the transition the way it's happening in this right hand side, right? So we get all the energy from the transition of that electron from conduction band to valence band. All right. So we looked at this idea in previous chapters that we can change the relative fraction of materials. When we did that, so here, like this subscript X, we are changing X. So what we are doing is we are going from fully aluminum arsenide to gallium arsenide. When you do that, the levels of these valleys of conduction band, they change. When they change, basically what we would be doing is we would be changing the levels of these things, these subbands. What does that mean is by changing that relative fraction, we may be converting a direct band gap material into an indirect band gap material and vice versa. So this is something, again, for a direct band gap material, this chi is what matters because this is directly like, I think it's sigma. It's directly lined up with the valence band minima. So if we follow that concept, so basically from here to here, everything on this side is direct band gap fraction of this. Anything from that side is then, because this X becomes lowest on this side, then in this case, this is indirect. So if you see this figure and you are given a combination of these fractions, so in the right, yeah, Magali, we can talk to her, no problem. Hi, how are you? We have we have been waiting for you all day. All right, fantastic. So it seems somebody learned something today because she was responsive or saying something. The rest of you are just quiet today. So okay, let me wrap it up. So this side is direct, and okay, do you see why I say left hand side from here is direct and the right hand side is indirect materials? All right, so it's changing with this fraction X. And that transition is happening somewhere X is equal to what, maybe 0.38. So if from aluminum 0.38, all right, that's going to be, let me just type it up. So aluminum, I don't know how to make subscript here. Aluminum 0.38, gallium, how much is 1 minus 0.38? 0.62, right? So this is the transition point. 0.37 and 0.61 would be direct because in that case, this valley is the lowest. Above that, this becomes the lowest as you follow this line, right?